Okay, so we have question 7 from the Step 2 2024 paper. It's basically a question about curves and finding intersections with a horizontal line. So yeah, if you want to try this question out, here's the full question. Yep, let's do the first part. So the first part is fairly simple, just sketch the curve C1 with this equation. So they've nicely given it in factored form and it equals 0. So whenever you have two factors that equal 0, you can say that either this this term equals 0. I just rearranged the 1 to get it on one side, and this equals 0. So these two equations make up the equation of a circle, right? They're just shifted along the x-axis. So if we just sketch that out, it will be something like this, where one of them is centered at -1 and the other one is centered at 1. For the next part, they ask us to consider the curve C2 with this equation. So very, very similar to what we had before, except instead of equaling 0, they have it equal as 1/16. And then they ask us to show that the line y equals k meets the curve C2 at points for which this equation is satisfied. And then they ask us to determine number of intersections between C2 and the line y equals k for each positive value of k. Alright, so let's just do the first part first. We just substitute y equals k into the original equation and then expand it out. So when we have y equals k, we get something like this. Then I expanded out the x minus 1 squared and x plus 1 squared terms. The 1's cancel out, so you get this. And then expand that out to get something like this. And when you basically simplify it a bit, you get what they have. So that one's not too bad. And then they want us to determine the number of intersections between the curve C2 and the line y equals k. Okay, so we basically have a polynomial of degree 4 in terms of x and k. But basically what we can say is that the solutions of x in this equation correspond to the intersections, right? So if you imagine the line y equals k is just a horizontal line, and when it meets the curve C2, it'll meet at some value of x and some value of y, right? That value of y will be k, but the value of x that it corresponds to will depend on k as well. So we're basically saying, okay, how many solutions for x does this equation have depending on the value of k, if that makes sense. Or I should say the other way around. Depending on the value of k, how many solutions of x are there in this equation? That makes a lot more sense. So yeah, conveniently it's degree 4, but it's in quadratic form. We just have x to the 4, x squared, and the constant term. So usually when you're working out the number of intersections, you, in A level at least, you usually work with the discriminant. But in this case, since it's step, you can try doing the discriminant, but that doesn't really help you. And that's because the discriminant is kind of like a worse version of the quadratic formula. Like, you lose a lot of information from doing the discriminant instead of just doing the quadratic formula. So let's use the quadratic formula and see what we can do for working out how many solutions there are for x. And that'll correspond to the number of intersections, right? So when you do the quadratic formula, it's not that bad, but you get something like this, and then you can simplify it. The 2 here cancels out with the 2 there, and then the minus I expanded out for this term. And then you can factor out a 4 from here. Square root of 4 is 2. That cancels out with the 2 here. So then you can just get rid of the denominator. And then you get something like this, right? So now let's analyze the discriminant, because that will tell us the number of solutions for x squared here. Remember, we want the number of solutions for x, not just x squared, but let's just start off with analyzing the discriminant. So this is the discriminant. Let's try and simplify it. You get it simplified to this. So the discriminant simplifies quite nicely to just this. And now what can we say about the number of solutions? Well, if we go back to what the original equation was for x squared, we have that x squared is equal to this, right? And so then there won't be any solutions if this is less than 0, right? So there's no intersections if this is less than 0 because you can't square root a negative number, which means that k squared, when k squared is greater than 65 over 64, there's no intersections. And it's good to keep things in terms of k squared instead of k, because then you don't have to worry about plus and minus, right? When you're taking the square roots of things. Yeah, so now if we consider when the discriminant is equal to 0, that would be when k squared is equal to 65 over 64. And that would mean that we have two intersections because there's two solutions for x. Imagine this was 0, then we have 2 minus k squared. And we know that is going to be greater than 0 because 65 over 64 is less than 2. So when we have that, it will be something positive. The square root of something positive will give you plus and minus something. And then that will correspond to two solutions for x. So yeah, when k squared equals 65 over 64, we have two intersections. Now we have to consider when this is greater than 0. So when it's greater than 0, you have that k squared is less than 65 over 64. And you can't immediately go straight to saying that there's going to be 4 solutions, right? Because we don't know whether or not this whole thing is going to be greater than 0. We know that discriminant is going to be greater than 0 if this is true, but we have to consider the two different cases, right? Plus and minus. So yeah, fortunately, when it's a plus, we know that this is going to be greater than 0, and we know that this is greater than 0. So that makes the whole thing greater than 0, right? So that gives us two solutions already. But then when it's a minus, we need to figure out whether or not that is going to leave the whole thing as positive or not. Because remember, we can't square root a negative number. So let's do some analysis on this. So we need to figure out, okay, when is this term going to be greater than 0? Let's try and simplify it by trying to get rid of the square root. So we move the square root on one side and square both sides. Remember, we can do that because both sides are greater than 0. And we know this is greater than 0 because remember, we're still working under the case when k squared is less than 65 over 64. Everything here is under the case that this is true. So when you square both sides, you get that you get this basically, and then it works out nicely. The k squareds cancel out, and you just get k to the 4 is greater than 1 over 16, which implies that k squared is greater than 1 over 4. So what this is saying is basically that if when k squared is greater than 1 over 4, we have two solutions for this, and we also have two solutions for this, right? So remember, the range is when k squared is greater than 1 over 4 and less than 65 over 64. That is going to be when we have 4 solutions. But we still have to be careful here because we haven't found all the solutions depending on what k can be. Like if we consider the range of what we found k to be, we know that we've considered the case where k squared is greater than 65 over 64 up until when k squared is greater than 1 over 4, right? So there's a range that we haven't considered between k squared is equal to 0 and k squared is equal to 1 over 4. So we got that k squared is equal to 1 over 4 from this inequality, right? But when you consider when k squared is equal to 1 over 4 exactly, then you get that this is equal to 0. And you can verify that by just substituting the value in. So when this equals 0, that corresponds to a singular value for x. But then you also have to consider this, right? This gives us two extra solutions. So we get 3 solutions in total when k squared is equal to 1 over 4. And when k squared is between 0 and 1 over 4, we get that this will be less than 0, right? So there's no solutions there, but this is going to be greater than 0. So that's just 2 solutions. But yeah, that was a lot of information. So just to summarize, we have that when k squared equals 65 over 64, we have 0 intersections. So that corresponds to when the discriminant is less than 0. So there's no solutions there. When k squared equals 65 over 64, that's 2 intersections. So there's 2 solutions for x. This will be equal to 0, and then this will just be a positive number. Square root it, you get 2 values. When k squared is between 0 and 1 over 4, we have 2 intersections because the negative case for here is going to be less than 0, but the positive case is going to be greater than 0, and that gives you 2 solutions. Then when k squared equals 1 over 4, you have that the negative case here is going to be just 0, and then the positive case is going to be greater than 0, so that gives us 3 solutions in total. And then the last case is then when k squared is between 1 over 4 and 65 over 64. That's the case when both the positive and negative give a positive value. So we're going to get 4 solutions there. Yeah, and this is this covers the entire range of k squared, right? Because k squared has to be greater than 0, and we've basically got it from 0 up until onwards, right? From 0 to infinity, basically. We've covered that entire range. And because we've kept everything in terms of k squared, right? Remember, originally that y equals k, right? And if we have k squared here, that basically just means that it's symmetric along the x-axis, right? So along the upper quadrant and then the lower quadrant, it's symmetrical, right? So that's the benefit of keeping things in terms of k squared. We don't get confused in terms of positive and negative. But yeah. Then for the next part, we have that they want us to determine whether the points on curve C2 with the greatest possible y-coordinate are further from or closer to the y-axis than those on curve C1. So where is the point on C1 with or on C2 with the greatest possible y-coordinate? Well, that's going to be, if we look at what our summary says, it's going to be when k squared, which k is equal to y, right? When y squared is equal to 65 over 64. So this is when we have the greatest possible y-coordinate of C2. So in other words, y is equal to the square root of this, right? But we don't really need to consider y here because we're trying to work out the x coordinate, right? We're trying to figure out whether or not it's closer to or further from compared to the y-axis, right? So we need to consider the x coordinate. So remember, we can work out the x coordinate using this quadratic formula here. So when we substitute the value of k squared, we get that x squared is equal to this. And when we square root it, we can see that it's going to be less than 1, right? Which means that if it's less than 1, it has to be closer to the y-axis, because curve C1, the greatest possible y value is going to be at y equals 1, right? And that's going to be an x coordinate of 1 because it's a circle of radius 1. So if we get an x value that's less than 1, that means that C2 is going to be closer to the y-axis. And then we have that the next part asks us to show that it's not possible for both this and this to be negative, and then deduce that curve C2 lies entirely outside the curve C1. Well, if this is negative, then we get these two inequalities, right? And what do these correspond to? Well, these just correspond to the regions inside the two circles. So x and y have to be in this region and in this region, but that can't be the case, right? Because they can't be in two different regions at once. If these regions are mutually exclusive, in other words, like the two regions don't intersect, they have an empty intersection. So since x and y can't be within both circles at once, that means that both these two equations they cannot be negative. And then for the next part, where they ask us to deduce that C2 lies entirely outside of C1, well, to do that we have to consider these two terms. So yeah, if we have two terms that equal a positive number and we know they're not both negative, that means that it can't be the case that one is positive and one is negative, right? Because then we would get a negative number. So then that means that both of these terms have to be positive. So if they're both positive, we get these inequalities, right? And if this is true, then that means that x and y have to be outside of these two circles, right? So it's basically the opposite case of here. These inequalities suggest that it's inside these two circles, but then this is the actual case, right? Where they have to be outside of those circles. And these two circles are C1, right? So C2 has to lie entirely outside of C1. And then they ask us to sketch C1 and C2 on the same axis. Remember, this is C1. And then if we could just consider all of our information. We can also notice that the curve is symmetrical in the x and y axis because we're just dealing with x squared and y squared. Then consider the individual values of k, which these are basically the horizontal lines when y equals k, right? We have that there's two intersections when y is this value. We have two intersections when y is this value. And then between these values. And then you can figure out how to sketch it however you want, but I mean, with this information, you just go through each of these regions, right? And then you know how many intersections there are, and you know that it also lies outside of C1. So then your final graph should look something like this, where we have three intersections when k is equal to plus and minus a half. And yeah, do the other things as they are. So yeah, that's the whole question. Honestly, I think this was quite a hard question, just because you have to consider so many different cases, and it's quite difficult to like make sure you haven't missed any. But yeah, that's it. Goodbye.